So similar to the comparison test, we're going to have a look at a couple different functions, one that we're trying to figure out, one that we know, and we're going to look at their limits though in this case. So here's what the limit comparison test says. If we have two series or two sequences, A sub n and B sub n, and we know the limit of the ratio of these sequences is a finite and positive number. So if we compare the ratio, A sub n over B sub n, so in other words, we're comparing them term by term basically. If the limit of that ratio is a finite number, then here's what it says. The two series either both converge or both diverge. All right, they're both going the same way. So that's the key. If we can compare them and we have a finite limit, then they're both going the same way. They're either both blowing up, divergent, or they're both converging. We don't necessarily know that they're converging to the same value. It just means that we know they're converging. And this is a pretty useful and powerful test. It's especially useful when we have two expressions that are fractions like this. So let's use the limit comparison test to determine the convergence of this function here. The sum of, from 1 to infinity, 1 over 4n squared plus 3n minus 2. And we're going to compare that to a simpler version, 1 over n squared. Okay? We know here that this one converges, right? Because this is a p series. Okay? So we're going to compare this. We're going to find the limit as n goes to infinity of 1 over 4n squared plus 3n minus 2 all over 1 over n squared. Okay, so we've got these two series. They're kind of similar. This is like a much simplified version of this. Okay, and so this is the limit as n goes to infinity of, well, if we multiply both sides, top and bottom, by n squared over 1, the reciprocal, right, we get one fraction, not a compound fraction anymore. Okay, plus 3n minus 2. Now, since these are both the same degree here, okay, and we're finding an infinite limit, those smaller degree terms don't matter. So the limit here is going to be 1 over 4, the ratio of the coefficients, since the coefficients are the same. So we get what we were looking for, a finite positive limit here. So since it's finite and positive, they either both converge or they both diverge. Well, we can say this. We know that the sum of 1 over n squared converges by the p-series test. Okay, it's a p-series with a n to an exponent that's bigger. The power there is bigger than 1. So since that is true, if we could put the word since this is true, okay, then we know that the sum of 1 over 4n squared plus 3n minus 2 converges, and we can say this by the limit comparison. All right, so there's our conclusion there. So the key here is this. We want to look for a series that is similar, that we do know the convergence of. All right? So we want to compare to a series that is similar, that we do know the convergence of. Okay? Because if we don't know the convergence of either of the series, then it doesn't tell us anything, right? All right. When we say we don't know the convergence, whether that means whether convergence of, that means we know whether it converges or not. So, all right. Well, that's the limit comparison. Again, we look for a similar series. We make a ratio. We find a limit to see if we get a finite number. If we do, they either both converge or both diverge. This turns out to be very useful when we're looking for something to kind of clean up a ratio with some powers in it. All right. So when choosing a P series, you must choose one with the same magnitude in the nth term. If it doesn't have the same magnitude, it's not going to work for us. All right. So here's some examples. If we start with this series like we just had, I think that's the same one we just had, and we compare it with 1 over n squared, well, this one converges, and it'll turn out these both converge. Okay. If we have this series here, and we compare it with one that's a kind of a simplified version, notice the 3 and the minus 2 go away. Well, this one diverges by the P series test, and so it turns out that these both can diverge. If we have a series like this, we might get rid of these smaller terms and compare this with n squared over n to the 5th, and which simplifies to 1 over n cubed. So these both converge because this one converges by the P series, and if you do the limit comparison, you'll see that this converges as well. All right, let's do one more example and call it good here. So let's use the limit comparison here to decide if this converges or not. So we have the square root of n over n squared. Well, let's compare this to the sum from 1 to infinity of the square root of n over n squared. And before we go too far, let's clean this up. This is n equals 1 to infinity of, this is n to the 1/2 over n squared. And that just simplifies to subtract the exponents. This is 2 minus a half gives us 1 1/2 or 3/2. Okay, and since this is bigger than 1, this converges. Now we haven't done our limit comparison yet, but we know that one converges, so we know it. That's great. So let's do our limit comparison. The limit as n goes to infinity of this fraction. We can take, doesn't really matter what order, we got n to the 1/2 over n squared plus 1 all over n to the 1/2 divided by n squared. Multiplying by the reciprocal there, this becomes on top n to the 1/2 times 2, so we're going to multiply by the reciprocal of this. You don't have to write it out, but I will just for our sake. 1/2 n squared over n to the 1/2. And that gives us n, we're adding powers there, n to the 5/2 all over, and if we distribute, we have n to the 5/2 plus n to the 1/2. Make sure you distribute it there. Okay, and since we're going to infinity, the smaller degree doesn't matter. We have the same degree top and bottom, and so this is going to go to the ratio of their coefficients, which is 1. Whenever we have the same degree on top and bottom, the ratio of their coefficients is our limit, and this is finite and positive. Okay, so therefore, the sum of n equals 1 to infinity, the square root of n over n squared plus 1 converges, because they either both converge or both diverge, and we just showed up here that this converges. Okay, we might say up here this is by the P series. So this converges by the limit comparison. All right, And that's how limit comparison works. So I hope that helps you to compare your series and find convergence in a new way. Thanks a lot.